The next thing which can happen in linear programming problems, well, actually it can happen in arbitrary optimization problems, is something which is called unboundedness. So let me again illustrate this issue on an example. So let us consider maximizing a function of two optimization variables subject to these two inequality constraints. Now, can you maybe just by looking and analyzing the problem tell me what the optimal solution is? Essentially, the optimum is achieved by increasing x1 and x2 as much as possible. Okay? So the question is, can we increase x1 and x2 all the way to infinity, or is there a constraint which stops us from going to infinity? Because obviously infinity here is the best solution. We are maximizing a linear function. So the maximum obviously is at infinity if we wouldn't have any constraint. So
in the first constraint there is minus x1 plus x2.
That's, sorry, it should be minus x1 plus x2. Yeah, here it should be plus x2. Yeah.
What is the value of infinity minus?
That's a good question, but let us not ask the question at all. Let us solve the problem. And we can solve the problem in two ways. We can solve it either using an algorithm, like a simplex algorithm, or we can solve it geometrically. So let us try the geometric method first. So let us draw the feasible set of this problem. Okay? So we have 4 inequality constraints. The first one is it is this constraint here, which means we are going into this direction, which means x2 must be larger than 0. Okay? Then we have also this constraint, which says x1 must be larger than 0. And the feasible set is the intersection of all inequality constraints. Okay, so right now we have this positive, or where to say non-negative ortant as the feasible set, but now we must add those two constraints. So we must draw the constraint is equal to 1 and x1 minus 2x2 is equal to 2. So let us draw these two equality constraints. And then we have inequality, so only one side of the constraint will contribute to the feasible set. So how would we draw this first constraint? So it's a linear constraint in two-dimensional space, so it's just a line. Okay? To draw a line, we need 2 points. One point we obtain by setting one variable to 0. So when x1 is 0, x2 is 1. So let's say this is 1. So that's the first point. And the second point we obtain by setting x2 equal to 0, and then x1 would be minus 1. So actually minus 1 is here. Okay? So it's actually this constraint. But now we have to determine, is it this side of the constraint or that side of the constraint? Remember here originally we had smaller than 1. Actually, the easiest way is to determine the location of 0 with respect to this constraint. If the 0 point satisfies this inequality, it would be this side of the constraint, which we have to consider. So 0, 0 is smaller than 1. So it is really this side. Okay? So now we already have this part as the feasible set, but we also have to add this constraint. So again, set x1 to 0. What would be the corresponding value of x2? It would be minus 1. So that's here. x2, 0. x1, 2. So it's this point. So it's this line. And which direction is it? Okay, so the constraint was like this. 0, 0. Smaller than 2. Okay, so this space must include the 0 point. Okay? So it's pointing in this direction. And now the feasible set is the intersection of those inequality constraints. And now look at, okay, next, because it is not enough just for the feasible set to be unbounded, for the problem to be unbounded, we also have to consider the value function. So how would the function 2x1 plus x2 look like? So how would you draw this equality constraint? Or, okay, let's do 1 here. Doesn't really matter. So draw it. Okay, so we fix x1 to 0. x2 would be 1. So it's again this point here. So that's for 0, and here that's 1, and here it's 0, and that's 1/2, right? So it's here, right? So that's the function that we want to optimize, and we are actually maximizing it, so we are going to move it into this direction. Now, where is now the optimal solution? At infinity. We can continue shifting this line here all the way to the right without a constraint stopping us. Okay? A completely different situation would occur if instead we would minimize 2x1 plus x2. Why? Because then we would go into the opposite direction, okay? And we would hit this point here as the optimum. Okay? So unboundedness has something to do with the feasible set being unbounded. Unbounded means there is no constraint stopping us from going in one of those directions. Okay? But that's just, it is not a sufficient condition for the overall optimization problem to be unbounded. It also must be that the cost function goes in the direction in which the feasible set is not bounded. That's what makes the overall optimization problem unbounded. Essentially what this means is that somebody asks you to optimize the profit and gives you a problem like this. Obviously this is an ideal situation from the profit side because we can achieve infinite profit. So essentially it means that probably the original optimization problem was not sufficiently well posed. But if this instead would be the cost of the production and we would minimize it, it doesn't matter that we are missing a constraint here. Since we would be optimizing in this direction, we would still find a solution despite the feasible set being unbounded. So that's the graphical explanation, and let us look at how the simplex method detects unboundedness and how we can deal with that. So let us form the simplex tableau. Okay? We know that to do that, first we have to convert inequality constraints into equalities. That's why we are introducing additional slack variables x3 and x4. We create the simplex tableau as the leading coefficients in front of the optimization variables in corresponding constraints, and then we put the cost function as the final row. Okay? And let us perform the pivoting operations. So which of these variables, by increasing, has the largest influence on the cost function? It's the one which is here. Okay? Which row is the most dangerous one? Which constraint will be hit if we start increasing x1? Well, we only have one choice. Because in the first row we have the coefficient -1, which means we are going away from the constraint. So we obviously have to look here. And we perform the pivot as usual, and we obtain this table. Now what next? Is this an optimal solution? No. So we have to pivot further. Which choices do we have for the pivoting variable? We only have just one choice, which is we only have one negative coefficient in the final row. Now, which constraint will be violated most, or the first one, by increasing x2? We start increasing x2. Will some constraints stop us from x2 going to infinity? No, because here we have all coefficients which are just negative. And this is how the simplex method detects unboundedness. Once after you perform a simplex iteration, and you see that in the pivoting column we have all negative entries corresponding to constraints, we know immediately that the problem is unbounded, meaning we don't perform any additional simplex iterations. We simply say that the optimal solution is when x2 is infinity. Well, that's not enough. We also have to say what is the corresponding value of x1. Okay? But x1 is here. Okay? 1 is 2, for instance. So x2 we can go to infinity without violating constraints. Therefore, also the cost function will go to infinity, and that's precisely what we have analyzed using the graphical solution. Okay, so we have function like this, and it goes all the way to the right. So unboundedness happens when there is no constraints which stops the objective function from increasing when we are maximizing, or decreasing when we are minimizing, to either plus infinity or minus infinity. Unboundedness is very easy to detect in the simplex tableau. In the pivoting variable, if we have all ratios which are negative, then we know that we have unboundedness. And actually, in practice, it usually means that our problem is badly posed. Okay, so somebody wanted you to maximize the profit and has forgot some constraint. Or you are minimizing the tracking error and somehow you forgot to restrict it from going to minus infinity. So usually unboundedness happens when the problem is not well set up. Okay? And it can usually happen, well, sometimes it happens in practice, but usually in economic optimization problems, if you detect unboundedness, you should alert the person who has created the optimization problem, because usually it means that he has done a poor job.